So the question asks what's the primary function of the EPC register in the thing, but the question was meant to ask the EPC of the trap frame, not the register.
Okay.
Okay. So the EPC of the trap frame, it stores the address of the currently executing function when the interrupt occurs. So when an interrupt occurs, the trap frame, the EPC of the trap frame will store the current instruction there. Okay, in the trap frame. When
Okay.
the interrupt occurs, we have to save the current context into that trap frame, right? The current thing, the current registers.
Right. Right.
Yeah, that's what this is saying. And so this is not about a question is should not be about EPC register, about the EPC of the trap frame. So that is that point here. So and it also holds the next address after the interrupt service, right? So in that case, this both are correct. So because we save the current thing, so that is the next instruction to be executed after the interrupt service, right? We haven't executed this instruction yet because we went into a trap. So we stored the value of the thing in that SEPC, right? When
Right.
a trap
Right. Yeah.
occurred,
Yeah.
yeah, the current instruction was in the SEPC and we stored it in the EPC of the trap frame. So that is also the next instruction to be executed after the interrupt service, right? We
Correct.
take that EPC from the trap frame. So this part is actually saying that we are taking the SEPC and putting in the trap frame of the EPC, right? So that's the line
Hmm.
that says when this is when the trap occurs. It's in the user trap function. When the trap occurs, we are saving it, right? And
Right.
then
Yeah.
here if it is a system call, then it would have been at the last instruction that have run is this eCall instruction, right? So that's why they have to go to the next instruction in the user mode. We don't want to call that system call again, right? So they move that. That's this line. So
Sorry.
one
Can you explain that incrementation by 4? That. Yeah.
4 is the size of the instruction. So each
Right.
instruction is 4 bytes. So when the eCall instruction is called from the user mode, we came from that instruction, right? So that's the current instruction. So we shouldn't be returning back to the same instruction because it will go back and call the eCall again.
Hmm. Okay. Yeah. Makes
So
sense.
that's why
Okay. So
we
you
are
go to the next one.
next one,
Okay.
right?
Okay, sir. Yeah. Got it.
Yeah,
So okay. So when you say that it should be the question should mention EPC of the trap frame and not the EPC register.
yeah.
Uh, if it were to actually mean the EPC register itself, what
So
would
in
have been
that
the
case,
answer in that case?
uh, in that case, actually EPC has the value. So like the SEPC register, right?
Right.
SEPC
Right.
register always has the values of the uh, program. So when an exception occurs, this SCP register will have the current instruction there.
Right.
EPC SEPC will have the current instruction that what the user mode was executing before the interrupt. The value of the program counter that in that case it will be the first I think yeah, the currently executing instruction.
So if it were only registered, then the last option would have been invalid in that case.
Uh,
The next instruction would not have been stored. Is that what you're saying?
in that case also, if you see, uh, uh,
Implementation anyway occurs, right?
yeah, you see the thing is the SCPC value stored here, right? So now when we go back, we write that SCPC back again from the EPC.
Right.
So in that
Right.
case also, the answer will be same. If we have mentioned SEPC register also, that it's not here, but it will when you come back from a trap, we write that contents of the EPC back to the SEPC, right?
Mm-hmm. Yeah. Yeah.
So that will also have the same answer. So that's the next instruction to run when after the service, right?
Correct. Correct.
Yeah. So
So
actually this
in either case, I mean,
this
as far as
yeah
these four options are concerned, whether it is asking about EPC of trap frame or just the EPC register, the answer won't change. The correct
yeah
answer
because
of
this
option A
this
and D.
yeah because this said suppose when it's going inside this is true, when it's coming outside this is true, right?
Right.
When we
Right.
see this thing.
Okay.
This
Yeah.
both
So
should be true in any case.
when you mentioned that it should be is EPC of trap frame and not the register, that is, I was confused as to what will be the actual difference in outcome between the two questions. So yeah,
No,
that's all.
so we don't have a EPC in like the register, right? It's SEPC and
MEPC.
thing. Yeah, that's why the EPC should be the EPC of the trap frame.
Okay, got
Okay.
it.
Okay. So any other things?
No, that was all from my end. So this SEPC and MEPC, they are similar to the SCOS and MCOS, right? One is supervisor mode and one is machine mode.
Yeah, yeah. So all the register will name like this only. All the supervisor mode register will have the S prefix, and the machine mode registers will have the
Hmm.
M prefix.
All right. Yeah. Okay, got it. Thanks.
So have you gone through week 8?
I have finished week 7, but not week 8 yet. Maybe others have done it, but I haven't completed week 8 yet.
Okay. Okay.
I'm briefly aware of the topics as such because I've already studied some of these concepts earlier, but I haven't watched the lectures yet. I'm yet to do that.
So okay. I think we have some of the problems like this in the graded assignment also. So this involves you to understand the code, like whether it will achieve. So if I say this now before you watch how the critical sections after solution, this section, I mean this two things, you won't be able to understand what it happens here. I thought I would explain these kind of things, but you also have a graded question similar to this one. So the main point is you should understand what causes mutual exclusion, what causes a deadlock, what is a progress, what is progress, and what is bounded waiting. These terms you should be aware of. Okay. So what exactly is this? Then you will able to solve these kind of problems. Okay.
Okay, will you walk us through the solution of this one?
So if I now walk us through a solution, I am not sure you will be able to understand these things because it involves like uh, if you have watched these two videos, you might understand the solution in that case. But
No,
if
you
you
can you
haven't
can
watched,
you can show the solution. I mean, you can walk us through the solution now, and anyway, we can come back to this. It's being live streamed, right? And I'm not the only one here. I guess Cherian might have also finished the lecture. So, I mean,
so okay. So in that case, okay, let me walk through this
because
question.
yeah, we have a similar question very similar to this one in the graded assignment as well.
Yeah, yeah. So okay. So you have this lock variable, right? So there is this two processes. So this is the code from the process one, and this is code from the process two. And you have four sections actually. So this is the we call this thing as the entry section. This is the critical section. This is the exit section, and this is the remainder section. So the think about critical sections are only one process should be in the critical
At a
section.
time. Yeah.
If only one process is in the critical section, it achieves mutual exclusion. So at a time, no two process can be in a mutual in the critical section. If there are two processes can be in the critical section at the same time, then it doesn't achieve mutual exclusion. So let's check whether this mutual exclusion is achieved here or not. So we have this lock, right? So here the lock can be either 1 or 0, right? By these values, lock can be either 1 or 0. So if lock is not equal to 0, in that case, so the lock is not equal to 0 means it won't be this process won't be able to enter the critical section, right? So only when lock becomes 0, this process can enter into the critical section. And after servicing the finishing the contents in the critical section, it will make the lock 1. And similarly, this process, it cannot enter into a critical section when the lock is 1. Okay, right? So lock can be either of these values. So assume the two
So
things.
mutual exclusion is not achieved.
Why do you say mutual exclusion is not assumed?
I mean, both. So if you have a, I mean, either case you will have only one. Oh, okay, okay, okay. Yeah, yeah, sorry, sorry. I'm sorry. Yeah, only one will
Because
enter the. Yeah.
so initially assume this both processes are started, right? So now lock is 0. So will this plus this is not equal to 1, right?
Yeah.
Then this process won't be able to enter into the critical section, right?
No, it is not equal to one, right? So
Yeah, if it is
so
not
it will
equal
at,
to 1, it will this is an infinite loop. This will wait here.
oh, okay, okay.
It's
Yeah,
not
yeah, yeah.
equal to 1.
It's a single statement. Okay, sorry.
Okay, so this is an infinite loop. These while statements are like busy waiting statement. Busy waiting statement in the sense it will loop again and again until that condition becomes false. This becomes false only when lock equal to 1, right?
Right. Yeah, yeah, yeah.
So until then, this will wait. So until lock becomes 1, we'll be waiting to enter critical section. We'll be waiting here to in the entry section. So this process too wants to enter the critical section, but it cannot because the value is 0. So that it's waiting to enter the critical section. So now what's this? Now this can enter, right? So this does the critical section, finishes the critical section, and then changes lock to 1. So now what happens? Now this process 1 is at remainder section, while process 2 can go into the critical section. These are happening in same. You can assume these two processes are running in different process as different processes in multiple processes or in multiple threads. You can imagine it like that. So these two can happen parallelly. Okay. So now mutual exclusion is achieved here in that case. So what is this thing? It could cause a deadlock. So deadlock can occur in some cases where both will be waiting. Both processes will be waiting for something to happen. So this will wait for something to happen, and this will also wait for something to happen, and that thing cannot happen. So this kind of situations may occur. So here in this case, actually deadlock is not there. But I think there is a case from this those the software solution attempts. So there will be 3 attempts that you will see. So one of the attempts, there is a deadlock is happening. I think let me go through that attempt where the deadlock is happening. Yeah, this part. So in this code, he uses something called as p1. There are two variables. P1 wants to enter equal to true, p2 wants to enter equal to true, and these things. There is this lock. If p2 wants to enter equal to true, which means if p2 wants to enter, this will wait. And if p1 wants to enter, this will wait. Okay. So assume you execute this line, says p1 wants to enter, right? And then a context switch occurs. So from here, you go here. And this line, you execute this line. So now, then you again come back here. So you check this. So what happens? P2 wants to enter, right? So this will be running in the while loop. It will be waiting. And when context switch occurs and you go here, P1 also wants to enter. So both want to enter, and both are waiting for the other process to finish and set this to false, right? Finish the critical section and set this to false. But both processes are waiting for the other's response. But so it caused a deadlock, right? Both processes cannot execute that. So they are both waiting for each other to go into the critical section in that case. So this process, this kind of solution could cause a deadlock. In this case, our solution is doesn't not causing any deadlock. So we will not select that answer. That is mutual exclusion. It doesn't cause this. So now let's see this statement. Process 2 can enter the critical section multiple times before the context switch if the process 1 is in the remainder section. So assume we are in the remainder section here. So process 1 is in the remainder section. So lock has become 1, right? In this case, lock has become 1. We finished the critical section, lock has become 1, we are in the remainder section. So there are multiple statements running there. We are not going back to the, we are not wanting the critical section, wanting to enter into the critical section for some time. In that some time, assume we are here, right? So we entered the critical section after this lock became 1. We entered this critical section and finished it. And now, after finishing the critical section, we set lock to 0. So assume no context switch occurs till now, and we finish the remainder section. Can we enter into the uh, critical section again without going here, without any context switch? We are still in the process. Still, scheduler haven't changed our context. So I finished the critical section one time. Okay, can I do that multiple times? So still now you can see the process 1 is not requesting the lock. Now it's also in the remainder section. So if it is in the remainder section, can I repeat this? So process 1 doesn't want the lock. So can I use the critical section multiple times? Is it possible here?
No, it's not.
Yeah, because this wants the process 1 to set the lock back again to 1 so that it can enter into the critical section again. So while assume if the process 1 has a very long remainder section and it doesn't needs the lock very often, this doesn't want to enter into the critical section very often, then what will happen? Process 2 also will be waiting for process 1 to enter the critical section again, right? So that's not actually the correct case. So this is what we are saying. Process can enter? No, it cannot enter. So it will be false. And this is process 1 will be always the first process to enter, that we said, because lock is equal to 0. Whatever context switch may occur, this will be the first process to enter, right? So that's true. And assume this question. So there are two processes, P1 and P2.
It will be process. Excuse me, sir.
Yeah.
It will be process 2 that will enter, right? It's lock equal to 0.
If lock equal to 0, this will be false, right? If lock equals 0, this will be true, right? So this will be waiting here. It won't enter into the critical section. Here it's an this one line is an infinite while loop.
So, are you missing the semicolon after that, Hemant?
Yes, sorry, I got it.
Yeah, I made the same mistake. So yeah, these while statements don't have anything within them, so they are just like
this while statements are just busy waiting loop. We call this as busy waiting loops. Okay, just waiting for something to happen.
I think there was a similar question. There was a similar question in quiz 1 as well, where a while statement did not have anything within it. So I made a similar mistake. I mean, I assumed that the lines below that while statement were part of that while block.
So,
we need to be careful with the semicolon.
Yeah, because we tend to use this kind of while statements more often in OS and this kind of multiprocessing things to wait. Okay. So now you see, okay, this question. So there are two processes, and if P1 can go into the critical section any number of times before the context switch, when P2 is waiting to enter the critical section, then which of the condition is not satisfied? So assume P1, this P2 is waiting to enter the critical section, means kind of in this place, in the entry section. P2 wants to enter the critical section. And assume if there is no context switch occurs, if P1 can go into the, while P2 is waiting, if P1 can go into the critical section any number of times, then what is not satisfied? So before that, we should be aware of these two terms. Like the mutual exclusion is a different thing that doesn't have anything related to this statement. So there is these two things: bounded waiting and progress, right? So what progress says is, so So assume there are two processes. So since there are two processes in this case, yeah, if process one doesn't request a lock, which means it doesn't want to enter a critical section, which means it's in the remainder section doing something else. It don't want to enter the critical section now. If process one don't want to enter the critical section, then process two should be able to enter into the critical section multiple times without wanting the anything from process one. So in that case, progress is achieved. So progress is when no processes request wants to enter the critical section, a process that requests the critical section should be able to enter it multiple times. If there are no other process wants to enter into the critical section, so then progress is achieved, right? So bounded waiting is kind of other thing to this. So if some process wants to enter the critical section, there should be a finite number of times where the other process can enter into the critical section before that. So this bounded waiting statement will be kind of confusing. So what in this two process case is that if this is requesting the lock, I shouldn't be doing entering the critical section again and again and again. That's what bounded waiting is says. So if other process is requesting the lock, I should be I cannot be I shouldn't be entering to the critical section multiple times. So there should be a bound like 1 or 2 or 3, a finite number of times. Any number of times means it's an arbitrary number of times, right? Not a bounded time. So if I could enter this multiple times without, since this is even when this is waiting, I shouldn't be able to go into critical section again and again and again. That's what bounded waiting does. So if bounded waiting is not satisfied, assume there are multiple transactions that occurs parallelly, and this wanted to make a change before this wanted to make a change again. So it should be given its chance. No, before that, this process shouldn't be able to take this again and again and again. So that's what bounded waiting says. All process should be kind of given equal fair chances. If I am requesting a lock, I shouldn't be waiting an infinite number of time. Okay, so assume two transactions. This one wants to enter into critical section first, and since the context switch doesn't occur, if this is doing changing this multiple times, then that's not what we wanted, right? So that's that bounded waiting time. It shouldn't be waiting so long to do that. So the optimal, the perfect solution should achieve mutual exclusion, progress, and bounded waiting. So if something could achieve these three of things, that's a solution to the critical section problem. And one of the solution is this bakery algorithm, and there is also a Peterson solution to it that we see here. So in this case, two things are there. If you see here, all these three things will be achieved. The mutual exclusion. So here actually, this is the original code. So this question is asking about something that is modified. Okay. So this is the original thing. So this question you need to think something like. So assume this. So if you are aware of the Peterson solution, so let's see what happens in this. So there are two processes. I denote it by process I in generally. So process 1 will have the choices 0, and process 0 will have the choices 1. Okay, and similarly this will also change, and here also 0 and 1 for process 0 and process 1. Two processes are there, right? Respectively. So instead of giving it like this, I gave it in a general form. Okay, and there are two locks and one choice. So what happens is, so there is this lock, right? So whenever this process I wants to enter, it sets the lock to 1. So it says process I want to enter. So here there is also this one more choice. So actually this Peterson solution solves the deadlock problem that we seen before. If both process want to enter, this choice will be either 0 or 1 from that thing. Choice cannot hold two things, right? So this condition will be in both of the process. So if both locks are 1, so if both process wants to enter the critical section, there will be this choice thing that makes only one process able to enter the critical section. So choice cannot be 0 and 1, right? At the same time, it can be at one. It can take only one value at a time. So it breaks kind of tie. If you see the Peterson solution, so you will know what this choice does. So generally in the Peterson solution, this choice favors the other process. So like if you see, this is process I, which is if it's 0, it favors the 1. And if it is 1, it favors the 0. So this question is, so in that case, all the three things are achieved. All this are achieved. You see, all this will be achieved in that Peterson solution. No deadlock will occur. Bounded weighting is there. Progress is there. Mutual exclusion is there. Everything is there. So what will happen if we change, instead of favoring the other process, if we favor the same process, instead of choice equal to 1 minus I, what will happen if you put I here? So that's the question. So could you tell whether mutual exclusion will occur? Will mutual exclusion will occur if it favors the same process? Any idea?
No, it won't. All the process will be stuck in this while loop, right?
No, choice can either be 1 or 0, right? So if choice is 1, at least one of the process will be false, right? So for one process, so for process 0, we are using choice equal to 1, right? For process 1, we are using choice equal to 0. Choice cannot be both 0 and 1, right? So at least one of this condition will become false, right? In both process.
Okay, yes.
So at least one of this thing will be thing, but not both. Both cannot be true at the same time, right? So in this case, mutual exclusion is achieved. Both cannot enter at the same time. One, at least only one will be able to, because this choice controls. If choice is true, one thing will be able to enter. If choice is false, the other thing will be able to enter. Not both, and not. It wouldn't cause a deadlock also, right? It also makes a try if it is favors the same process. But what happens? So let's think about progress. So it doesn't cause a deadlock. So this, if you change the choice also, it won't cause a deadlock, because the choice will be, it at least one loop will break, right? So at least one loop will break, so that uh, makes this deadlock free, and both cannot be true. That makes this mutual exclusion is achieved. And then what? Let's think about this progress and bounded weighting. So in progress, if one process in the remainder section, the next process should be able to go multiple times, right? So assume the process 0 is in the remainder section. So now lock of 0 will be 0. So process this process I between process 0 don't want to enter the critical section. So now if process 0 don't want to enter into the critical section, this lock of 0 will be false, right? Yeah, so lock of 0 will be false. So assume that case. So what will be there? So lock of 0 is 0. And assume if this process, the other process want to enter, right? That other process, okay, I see. Oh, it should be here. Here it should be I, not 0. So since we are doing this, right? Yeah, now I see this. There is some small correction here. This should be lock of I. Since we are using this generalizing that, it should be process I. Actually, this should be. Let me think. Okay, it should. Okay. Okay, it should be. I think it's around here. It should be a 1 minus I there also. And that. Yeah. Yeah, it should be 1 minus I in that case. So there was a problem there. Okay. Okay, we'll change it there. There is that. Yeah. Here it should be a log of 1 minus I. So like while that wants to enter, I will wait. And while this guy wants to enter, that guy will wait. So it's kind of that. Okay. Okay, yeah, that should be the log of 1 minus I. Okay. So okay, in that case, so now assume. So if I set this log to 0, so there assume this is 1 minus I. So log of I equal to 0 means there 1 minus I will be this thing 0. 1 minus I in that process will be 0, right? So while this doesn't want to enter, you can see that this loop will break in the other process while I am in the remainder section, right? Anyways, if I am in the remainder section, that can enter multiple times because this is 0 while I am in the remainder section and I don't want the lock. So lock of 0 where lock of 1 minus I equal to 0 in process 1, right? So that guy can enter multiple times. So there is progress. If I'm in this, I don't want this, this guy could be able to do this multiple times. So there is progress. So progress is achieved. So what's not achieved is bounded waiting. We'll see why. So assume so we have to change this, right? We have to change choice equal to I. I this thing. Instead of 1 minus I, we'll be setting it to I here. Now what will happen? So this wants to enter. Assume this wants to enter, and that also wants to enter. And I prefer this process. And now he wants to enter, but I don't care about this. But this choice is true, right? Because here we'll replace I. So choice is I, and then what will happen? We can enter this. We don't care about whether he is waiting or not. We'll enter this. Assume no context switch occurs. Now we'll see this again. We'll go here again, and this choice will be I. And we see this will be also equal to I, right? Even though this guy I minus 1, which is lock of 1 in process 0, wants to enter, we can go here multiple times since that choice is equal to I. But if choice is equal to 1 minus I, we have to wait here and go to that process and check if he also wants to go, and it will go like that. So when we set, when we choose the same process, the bounded waiting condition is not achieved. This guy can go here multiple times even if that guy wants the lock, right? In that case, we will correct this to this. And actually this condition should be also I equal to 1. So it's like that. Both these places, what happens, this question is about what happens if this I 1 minus I is replaced with I. So that's what the question is. And here there is a mistake, so we'll correct this.
So there's only one mistake, right? Instead of a lock of 0, there should be lock of 1 minus I.
Yeah, and the question, if the choice is set to I instead of 1 minus I, but it should be also checking I instead of 1 minus I. This is what, this is only this part is given here. changing this part is given in the question, we should be also changing here also. Instead of 1 minus I here, there should be I in the sense, no, not in the question. So what I am saying, so here I am saying to replace, right? So due to this, I am only saying to replace this thing, 1 minus I to I. But the question should also have a line saying that to replace this condition also. So that is not a mistake in this part of the question, and the mistake here in the code is only this part. Okay. Kind of able to understand. So here it should be 1 minus I. And what I am saying is, here it will be 1 minus I, right? So if we set favor this our own process, and here also we should be favoring that process, right? So changing this 1 minus I here and here. So the question is to change, right? What happens if you change this? So it's only asking you to change this part to I, but it should be also asking to change this part. So this is the mistake in the question, and this is the missing part in the question that asks you to change the choice to I, choice to check the choice with I. Okay. Is it okay?
Okay, okay. Making we should change both of them, then only it will work. Sorry, you are saying
Yeah,
right?
yeah, because if choice is equal to I and this is equal to 1 minus I, okay, let's see. If choice is equal to, okay, let me think. If that 1 minus I don't wants this log, I assume he wants this log, and you set choice equal to 0. Okay, okay. Yeah, this part is fine actually. Okay. This is I. This is I. As okay, let's assume this is I, and this is 1 minus I. So 1 minus I equal to true means this process wants the log, and choice is 1 minus I. So now choice is I, so this will break, right? Okay, you don't have to change it here. Actually, you don't have to change it here. You only have to change. So that's okay with the question. That part is okay in the question. Only this part is the problem. Yeah. So assuming if you put I here, this will break, right? Instead of that breaking, this will break. So you have to only change the by the question. You should only change I here, and the mistake in the code is here log of 1 minus I will come. Here it's 1 minus I only. You don't have to change here.
Okay, okay.
Okay. Yeah, that's 1 minus I. Yeah, fine. Okay.
So I was having doubt in week 7. If you can
Yeah,
explain that.
yeah. What?
Basically, regarding the IO bound and CPU bound process, we are dynamically adjusting the time slice, right, for the CFS scheduler.
Which scheduler?
CFS scheduler.
This one.
Yes.
Could you repeat that? What? Could you repeat the question?
So my doubt is for the CFS scheduler, why is it increasing the time slice for the IO bound process? Because the burst time, it means that IO bound process takes less time, right, to execute. So why are increasing the time slice?
IO bound process. Why do you think IO bound process takes less time?
It was mentioned, and it says that it usually takes less burst time, less cycle times to execute.
Okay. Let me go through it. Can you point it where is that? Here.
Yes, here, yeah.
Okay.
So I find these two statements contradictory, right? They have low
Here.
burst time, but we are giving them large time slice.
Okay. So the burst time is the time that it's actually running on the CPU, right? So usually what IO bound what it says is uh, it has small burst time. That's okay. So what is this time slice in this computer? Okay, okay. What's the time slice? What's the time slice here?
The time slice,
means that 2 units or 1 units that round robin.
it was adjusted dynamically using priority. If priority was less than 120, then time slice would be given more.
Okay.
Can you repeat the question? I did not understand what is the doubt actually.
So my question was, if a IO bound process takes less time on an average, then why are we giving it a larger time slice as it is given in the slide?
Maybe because like I have bound like more frequently used or something.
So here is this right. Yeah. Okay. So we give this V runtime is the time slice, right? What is the time slice? This V run. So we assume a virtual runtime for that, right? How long it will take to run this? That's what virtual runtime is, right?
Actually, so the equation for the time slice is not given for the CFS scheduler, but for the O of one scheduler, it was given.
Okay. Okay. Then I think we'll check this and maybe you raise a discourse post. We'll check this and discuss that there.
Okay, sir. Okay.
Yeah. So any other things?
Yeah, could you check the Google Meet chat box? Cherian has raised a
Okay.
question long ago.
5. PA5 in the sense which week?
PF5 is week 5. Week 5
Yeah, week 5.
27.
Which question number?
That he has not mentioned. Cherian, could you mention the question number?
Okay.
Actually,
This one.
he was asking about the.
Which one?
He says, I think it's question 1. That is what he put out.
Here it's I think
Okay, no, this is. Did you mean question 11 or something like that?
is it PA this week only? Because I don't see anything related to that RGA.
Okay, he says, sorry, must be PS6. I don't have access now.
Okay.
Could you check PS6? He's asking about M time and M time CMP. Is it
This
greater
one.
than or greater than equal to? Okay, yeah, this is PS6 question mark.
Okay, let us check when an interrupt occurs. So in the start dots is start dot c timer when it happens, and there's this timer, right? Okay.
Cherian is saying that the website that was shown in the previous live session had greater than and equal to, but the PA has just greater than.
Which website?
I'm not sure of that. He mentions that there was a website that was shown in the last live session.
It was, I think,
Okay.
5mdev.
Okay, let me check this in the code. So this is the timer init function. That's just the interval, and kernel work. Okay, this raises see, Clint raises the timer interrupt, and timer rec handles that interrupt. So it adjusts that and raises this. Okay. So when does the interrupt happens? When it is equal to or this? So your doubt is about this or this, right? Okay. Let's check. Okay. So which website it was shown? I am not sure what which website. Okay, let's check here. In this timer interrupts.
Can you check the chat box again? Hemant has shared a link.
Okay, this one.
Yes, I think the second paragraph from the start.
Yeah, value greater than or equal to, it says.
Okay. Okay, then it will be greater than or equal to. Oh, is this that answer is given as greater than? Okay. Yeah, then it's greater than or equal to only. Yeah. Yeah. Machine timer interrupt occurs whenever this. Okay. So that's greater than or equal to. Okay, that's correct. We'll change that.
Hemant, that maybe like IO bound process a higher priority, right? So for higher time slice, maybe like like CPU want to ensure like more time that they are not waiting or something. They are not disturbed. Hello.
Yes, yes.
So maybe like whenever they need like IO bound process, they will can execute and maybe because of that.
Okay.
So that's the one reason. Like, did you got it or?
Okay, actually, do we need to is there some resource to learn about that, the details of the CFS scheduler? Because in
CFS?
the slides it is given in very just verbally it is given.
Correct. So maybe like there is a one operating system book. Maybe I'll share that book. That Galvino CFS scheduler is given more clear. Like Galvino, if you search in that Google.
And a general doubt for
Silver
what type
Sats.
of
Yes,
The book you are referring to?
Galvino. Okay.
Yeah. Okay. Yeah, the same one.
So, yeah. So maybe you can like just go through that CFS scheduler. Okay, any doubt? Okay, so if you have any doubt, post in the chat box or in the Discord. Will
just one more. Does priority is used in XV6
like can you
because the scheduler is only just going through the array of procs, right?
So basically, XV6 we use round robin because the timer interrupt occurs and we change the process at a specific interval in a we simply loop through it and select the next process available, right? And which is round robin. It is just round robin. If you see the scheduler code, it will be just going through the loop, selecting the first process that is in the ready state, which is you can see the scheduler code in Clockdot. Right. Simply we are running a for loop, find which process is runnable, then we run it for some times until the next timer interrupt occurs, right? We don't do anything fancy, give priority or something like that. It's just basic round robin.
Okay, okay.
Okay, then we can wind up the session. Thanks for joining. We'll meet next week.
Yeah, thanks.
Yeah.